Hey everybody, it's Friday, 12:05. Yay! Another brown bag. This one by Lauren Schmidt. Yay, Lauren's been to Norway, so she's got to tell us a little bit about what Norway looks like, but also tell us about the exciting research that she's been doing with Nick Glacial. So Lauren, up to you.
Okay. Hi everyone, thank you for coming. So I wanted to talk to you about my research in Greenland, but first I feel like I need to provide some climate context for you all. So I'm sure you all are aware of like the severity of climate change currently since the industrial era. But you might not be aware of is this process of Arctic phenomenon of Arctic amplification, which is the warming of the Arctic 3 to 4 times the global average. And you can see on that figure there that most of the Arctic is situated within that reddish to orangish color, meaning it's warming at an extreme rate. So that's causing accelerated ice sheet melt, glacier melt, and ice cap melt, which is contributing to the overall sea level rise. It also has links to lower atmospheric circulation patterns that we can see. So some questions still remain about what this Arctic warming is going to be doing to these regions and what impact it's going to have on the environment. And we can use paleoclimate data to kind of get at that. So northern Greenland is a really good place for figuring out this climate data. So I was working in an area called Peary-land. It's the northernmost region in Greenland that you can get. And you can see at the image on the bottom left of the study site, actually, it's a very barren place, lacks vegetation. There's not a whole lot going on there. It does have a lot of ice caps and glaciers, which are being influenced heavily by the warming of the Arctic. And temperature data from northern Greenland has shown that there's a 3 degrees Celsius increase in temperature just in the past 60 years. So that's a very concerning figure. Unfortunately, our instrumental record only goes back to around the 1960s. So one of the goals I had initially was to try to extend this somewhat. And to do that, we actually worked on a lake called Lake Southwest, and it's just right there in the middle. So a relatively small lake, but there's ice caps to the north and south that are contributing to sedimentation within the lake. They're still within the catchment area. And generally, this area is predominantly dolomite, siltstone, and sandstone. But you can see even more with this figure that it's just all bedrock, no vegetation at all, and covered in ice and snow. So Lake Southwest is a proglacial lake. So what that means is that it's a lake that sits on the margin of a glacier. And glaciers, by definition, have internal flow and internal movement constantly. They also release meltwater at the bottom of the glacier, and that's going to flow down the bedrock and erode away and deposit it into the lake. So these lakes are really high-resolution sediment archives that we can look at to piece together glacial and interglacial periods. And sedimentation within the lake itself is going to be directly influenced by that glacier that's either, in the case of Lake Southwest, either to the north or south of it. And it's also going to be influenced by lake ice cover and changes in lake levels. So Lake Southwest is a really good site because it's a proglacial lake. It has no vegetation around it, which is unfortunate in some ways, but it also is situated in this Arctic region that's experiencing extreme warming. And that's really beneficial for some of my research goals. So one thing I wanted to do was develop a paleoclimate record of the region using the Lake Southwest core. So to do that, I first established a chronology for the lake, and then I took a look at the physical sedimentation within the lake to kind of figure out what was going on in the environment surrounding it. So to do that, first sampling and descriptions of the core were required. To try to date the core, I utilized cesium and lead isotopes, which are very short-lived isotopes, spanning the last 150 years. So that's going to provide a good dating for the upper section of the core, which we can then extend backwards. Radiocarbon dating was attempted, but it was unsuccessful just because there's no organic material getting into the lake. So that didn't make it into the research. And then for the physical sedimentology part, X-ray fluorescent scanning was used to determine how the changes in the elements throughout the core, and then grain size analysis was used. So for the sampling, we had this 1.5 meter long gravity core recovered from the lake. And from that, the upper 15 centimeters were used for grain size analysis, where we sampled every 0.5 centimeters. And that was dried sediment to be processed and put in a particle size analyzer here. So these are actually images from my work in Norway, where I was working on a lake to the north of Lake Southwest. So it was a very similar process for sampling, just on a different lake, different sorts of things going on. So to actually get at how old this lake was, we utilized lead-210 and cesium-137 analysis. Cesium is actually a radioactive isotope that's a product of nuclear weapons testing. So it's present only throughout this very short period of time. And it has a known peak in 1963. So we can then look at the data here. And you see this peak right here is correlated to about 2.75 centimeters down the core. So just within the top 3 centimeters of this core, there's about 60 years going on. Lead-210 analysis was also done to help support this cesium plot. And then another researcher on the project also did counting of barred layers, which is essentially a seasonal layer related to spring thaw and summer freeze. So it's just within this one layer. And so all of that helps to kind of establish what sort of time period and sedimentation rate we were looking at. And then that was extended further down the core. So here's a picture of the core I was actually working on. You can see that, so the top is on the left side and the bottom's on the right side. This is spanning around 3,500 years or so. Just taking a look at it, it's a very finely laminated core. And there's a color change with darker colored sediments towards the bottom, and it progressively gets lighter as you move up towards the top. So we took this core and we put it in an X-ray fluorescent scanning instrument, or XRF machine. You would put it in sort of to the left side, and in that box, it would then send it through the instrument. And then on the little box area in the middle, there's going to be a laser that shoots down on the core, the surface of the core. And because of some stuff I don't completely understand, there's a elements react at different levels to the laser input. And so we can then look at that fluorescing and how brightly it is to determine how the elements change throughout the core. And then that produced a 10 elements, and we could then compare it and see how it changed. And then I just wanted to draw your attention to that really thick, or relatively thick, band of dark sediment. We're kind of thinking that's a result of glacial input into the lake. And then these were all actual results from the upper 15 centimeters of the XRF scanning. So here you have a section of the core on the left, an image of it. Density, PC1, titanium, and calcium are plotted. Titanium and calcium were selected out of all of the 10 elements because they correlated really well with PC1, which that's a result of a principal component analysis, which is essentially a statistical analysis used to take this huge data set that we got from the XRF data and condense it into something more manageable, and we could see the trends throughout. Unfortunately, we didn't see much long-term trends throughout it. There was either throughout the upper 15 centimeters or throughout the entire core. So that was a little bit disappointing. But we did get really good data from the grain size analysis. So Lake Southwest is made up of mostly sand, silt, and clay. And through the upper 15 centimeters is about 200 years of time. And on that, we could establish three periods of sedimentation throughout. So over the first 200 years, it's mostly clay and silt. And then in the 19th century, sand-sized grains start to appear, but it's not until the last 100 years that we're seeing coarser grains and sand grains start to appear. So overall, there is a coarsening upwards of the sediment, which I'm going to go back to for why we think that's happening. So overall, I want to briefly go back to the elemental data from the XRF. And we have some idea of, or at least we're trying to determine why there's really no long-term trends within that data. And we're thinking it's could be that these glaciers that are surrounding Lake Southwest are particularly insensitive to late Holocene climate trends. Or it could be that there's a lack of sediment production and input into the lake that would provide such trends. Now with the grain size data, we're thinking that that period of coarser sediment over the last 100 years is could be a result of increased runoff to the lake as a result of anthropogenic warming over recent time periods. It could be that the lake itself is ice-free for longer and allowing more sediment to actually be inputted into the lake, or just glacial retreat. So we did see, like I said, we did see really good results with the grain size data, and other research done looked at diatoms trends within Lake Southwest. So here's preliminary data from one of the other researchers on the project, and different species of diatoms are plotted on the x-axis, and then on the y-axis is years. So we kind of superimposed those 3 periods of sedimentation onto this to see if there was correlation between it, and we did see a really good correlation. Over the first 200 years, there was very few changes. It was very stable in the diatoms. It was in the 19th century where we saw those that input of sand-sized grains start, where we see a rise in benthic diatoms. And then over the last 100 years, where we see that really coarse grain sediment appear in the lake, we see plantotic diatoms start to show up. And you can see on the that red plot all the way to the left, that's the plantotic diatoms, and they just really don't appear prior to the last 100 years or even a little bit later. So that was one of the really good results we got from all this data. But what does all this mean for Lake Southwest and Northern Greenland? So there's the idea that the glaciers that are actually draining into Lake Southwest are cold-based glaciers, which essentially means that they're frozen to the bedrock. There's not a whole lot of meltwater being inputted from the glacier, and so there's a lack of sediment input into the lake, which will kind of explain the lack of long-term trends we're seeing within the elemental data. And generally, cold-based glaciers are not very sensitive to seasonal variations in temperature. So that would kind of follow really well. The other idea we have is related to lake ice cover. So as conditions start to warm up, changes in how long the lake is covered in ice would influence how much sediment can be inputted into the lake. So if there's more months out of the year where Lake Southwest is not covered in ice, then there's more of a chance for coarser grains to be inputted into the lake, which is kind of what we're seeing over the last 100 years. And again, that's very consistent with the diatom data. So like all research, there's still much more work that needs to be done just to determine if what's going on here is a trend that's like localized or isolated to Lake Southwest, or if this is something that's more regional and broader to Northern Greenland.
Okay,
And that's all I have. Do you have any questions?